Now, whenever we float a boat, it's important that the boat doesn't capsize, that you don't put too much cargo in a boat so that the water comes up over the edges. And one factor that plays a key role in that is Archimedes' principle. But Archimedes' principle is premised under the idea that, hey, we only can displace, we can only provide a buoyant force equal to the weight of the water displaced. So in our second lab day, we're going to pretend that this little petri dish is a boat. And we're going to determine the volume of this boat. And from that, we're going to determine the mass of the water that is pushed off to the side by this boat. Because if I sink this in right up to the rim of this, that's going to equal this amount of weight of the water that's pushed off to the side. So let's first figure out the volume of this container. And the volume is equal to pi r squared times the height. So the very first thing we're going to do here is determine what the radius of this container is. And since the diameter of this container is about 8.6 centimeters, that means that the radius is 4.3 centimeters. So on your lab, enter that for the radius. Second thing we're going to do is we're going to figure out the height of this container. So the height of this container looks like it's about 1.4 centimeters. So we are going to use a formula to figure out the volume of this container. And the volume of a cylinder is area times height, or pi r squared times height. That's going to give us the volume of this container. Why don't you tackle that right now? Now the density of water happens to be 1 gram per cubic centimeter. So on the first problem, if I knew what the volume of this was in cubic centimeters, I know the mass of the water that would be displaced. Because 1 gram of water is 1 cubic centimeter of water. So if I push off to the side 5 cubic centimeters of water, that means I'm displacing 5 grams of water. So your volume in cubic centimeters is going to equal the mass of the water displaced in grams. It's kind of a neat deal. So why don't you figure that and pass that down. And then the lab asks you to figure out the mass of 1 penny. So we'll do that right now. And the mass of 1 penny happens to be 2.5 grams. Okay? You can see that on your lab right there. It's now it's back to 2.6. Let's call it 2.6 grams. Okay? Write that in. Now, based upon the fact that the buoyant force equals the mass of this water displaced, and the fact that every single penny has a mass of 2.6 grams, I want to know how many pennies I can put in this petri dish in water until this capsizes. So what you're going to do is take your volume, your mass of the water that would be displaced by this, and divide it by the mass of 1 penny. Divide it by 2.6 grams. That will tell you how many pennies you can fit into this boat before it sinks. So calculate that quickly. So now we're going to see whether Archimedes' principle works. I'm going to put in this petri dish. It's currently floating. And I'm going to add 1 penny at a time until it sinks. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. I was able to fit in 26 pennies. How does that match your prediction?